Hi, everyone. We're going to get started in just a minute. We're going to let people continue to join. You want to say hi in the chat while we're waiting to get started? That'd be great. All right, I think we'll get started. Welcome everyone to Digital Design Addressing the Ecological Crisis. I'm Claudia, your co-host for today's event. I'm the chair of the Toronto BIM community and the director of design technologies at Diamond Schmidt Architects, along with Patrick, the chair of the Dynamo user group, Toronto Dynamo user group. Next. So we're excited about today's presentation. This is the second collaboration between the Toronto Dynamo user group and the Toronto BIM community. Today's event is sponsored by Intuitive and Diamond Schmidt Architects. So before we get started, I'll just give a quick agenda. We're going to do a quick introduction, and then Patrick's going to provide a forward setting the tone of the discussion and giving some definitions and for terms that will be used through the presentations. Then we're going to have all of our panelists do about 10-minute presentation, and then we're going to open it up for a moderated discussion and then close it out just before 2 o'clock Eastern time. So today's event is eligible for continuing education. So if you're interested in OAA continuing education or CANBIB certificate for continuing education, please reach out to the Toronto Dynamo user group, the email below, committee@torontodug.ca for a certificate following today's event. So just a little bit of housekeeping here. Again, we have people joining from all over, so please say hello in the chat so everyone can see who's attending this event today. And if you have any questions, also use the chat. We will be looking at the questions during the moderated discussion, and we'll try to answer them. This session is also being recorded and will be available on the Toronto Dynamo user group's website shortly. So a little bit about the user groups. The Toronto BIM community is a local network collaborating across all facets of the industry with focus on implementing BIM and digitization of our industry from design through construction and into operations. We recently released the BIM report in the end of 2020. So if you want a free copy of the report, it's a benchmark of how Canada is doing with its BIM implementation. It's available on tbimc.ca.
Hello, everyone, and welcome. My name is Patrick Woźniczka, and I am one of the founders of the Toronto Dynamo user group. I am a computational design specialist with a master's in architecture, and I will be co-moderating our discussion today with Claudia. Toronto Dynamo user group is a community of visual programming enthusiasts striving to stimulate the exchange of innovative workflows and promote computational design. We are a Toronto-based group with a local focus, but we often tackle issues that exceed local boundaries. And I'd like to thank international guests for joining us today and invite them to actively contribute to our discussion and share their insights in the chat. We operate through our Slack workspace, which is connecting our community daily, YouTube channel where we post recordings from our events, and the website which provides easy access to all the good content that we created. Let me briefly talk about who joined us today. We have approximately 250 registrants from across 150 institutions. The international makeup of the registrations contributed to a large variety of job titles, but in an attempt to simplify, we can say that we have architects, engineers, builders, owners, and representatives of academia and fabricators. Before I will introduce our panelists, I'd like to share a few thoughts with you in order to set the stage for our discussion. First, I'd like to briefly explain why we chose this topic. We were inspired by a sense of urgency amongst peers and a notion that environments we build are not up to the task of creating a sustainable habitat for generations to come. To justify our decision, with a credible source, I have this excerpt from Fabricate 2020 that declares digital design and construction technologies to be central in our response to the climate and ecological emergency. In this 5-minute forward, I'd like to focus on 4 concepts and share important perspectives that I hope will string our discussion together. I am not interested in theoretical deliberations or disputes about the nature of the generative, the parametric, the algorithmic design, etc. I am interested in the practical potential of certain perspectives. Let's start with computerization. New Leach uses that word to describe the period when old analog techniques were transferred into a digital domain, the beginning of use of computers in architectural offices. And then he adds that computerization is the act of storing information in the computer or a computer system. Computation, on the other hand, is more than that. It is the procedure of calculating, determining something by mathematical or logical methods. For architects, engineers, builders, computation begins when they begin to use computers to understand material and structural behavior. This distinction is important because it leads to a shift in thinking. Form is not a result of arbitrary decisions anymore, but is being derived from material, structural, and environmental information. One of the most rigorous and succinct distinctions between computation and computerization I found in this book edited by Aki Menges and Sean Alquist's Computational Design Thinking. Using their words, computation represents methods that deduce results from values or sets of values, while computerization describes methods that simply compile or associate given values or sets of values. If we're not using our tools to deduce our designs from the data that we have at our disposal, we're not using the tools that we have to their fullest capacity. Computational design begins when we construct systems of formally described relationships. One of the famous examples of such systems is Gaudi's analog parametric design computer. He explored some of his designs using scale models made of chains or weighted strings. They took him years to build, but gave him more flexibility to explore organic designs, since every adjustment would immediately trigger the physical recomputation of optimal arches. To summarize, computational design thinking helps designers make sense of loopy, complex systems, chunk big problems into smaller, more solvable parts, devise design systems that integrate environmental performance, manufacturing constraints, assembly logics, and material characteristics, and deduce form from those relationships. Manufacturing, assembly, and disassembly can be engaged with the environment, materials, structural, and architectural systems by means of computational design. Fundamental concepts which underlie computational theory and techniques expose form as a subsidiary component of environment. The upcoming presentations and the following discussion will help us understand how to harness information from environment, materials, and construction systems in order to construct with them our design system that have the capability to deduce shape, behavior, and the environmental impact of the artifact that we design. Now I'd like to welcome and introduce our 6th panelist. Terry Peters is an assistant professor at Ryerson University, where she currently teaches sustainable practices, design studio, lighting design, and design for health. Brady Peters is an assistant professor at the University of Toronto, specializing in computational design, information technology, and architectural acoustics. He is also a director with Smart Geometry, and before starting his career at academia, he was an associate partner at Foster & Partners and a member of their famous specialist modeling group. Tristan leads the advanced performance analysis team at Intuitive and has been engaged in the thermodynamic simulation of buildings for over 15 years. Since migrating to the world of sustainable design over a decade ago, he has applied his talents to improving the energy efficiency of our built environment. Shada Shahi is a licensed architect, lecturer, and a PhD candidate specializing in circular economy design and implementation for the built environment. Patrick Chouinard is a founder at Element 5, where he's helping revolutionize the way buildings are designed, engineered, and constructed, using innovative construction methods and materials. Nick Zeeb is a senior design and cost consultant at Element 5. He's a hardworking and dedicated engineer, and before joining Element 5, he worked as a computational design lead at Intuitive. Okay, time for the good stuff. I would like to invite our first panelist, Brady Peters, to start their presentation.
Hello, everybody. Hope you all can hear me.
Yes.
Great. So thanks to Patrick and to Claudia for inviting us to speak at this event. So the presentation that I'm going to give today and my co-author, Terry Peters, is going to give is based on our 2018 book, Computing the Environment. So I'm going to see if I can share my screen here. Just one second. Okay, hopefully everyone can see this now.
Yes, all good.
Oh, excellent. Okay, so this photograph is called Earthrise and was taken by astronaut Bill Anders in 1968 during the Apollo 8 mission, 7 months before the first lunar landing. This was one of the first photographs looking back at the Earth. Here we see the Earth as a finite closed system, with its nearest neighbor, the Moon, a desolate surface in the foreground. The Earth is revealed to be vulnerable in the infinite vastness of inhospitable space. As Carl Sagan wrote, the Earth is the only world known so far to harbor life. For the moment, the Earth is where we make our last stand. So we only have one Earth, so let's protect the environment. But this meeting today is about buildings. So what does architecture have to do with the environment and with climate change? Well, all buildings, even the most sustainable, use energy resources and produce emissions. So this is clearly one way that architect impacts the environment. However, I would like to take this discussion in a slightly different direction. The definition of what it means to be an architect is linked to design tools. As Jonathan Hill has pointed out, it was the invention of drawing that enabled the creation of the architect. Being an architect is defined by our ability to conceive of, to draw, and to communicate the plans for a building at or removed from construction. However, architects no longer draw on the drafting board, but now with the computer. But the computer is not the same as the drafting board, as Patrick has pointed out earlier today. And so with changes to our drawing technology come changes to our profession. New tools mean new ways of thinking. As computer scientist Alan Kay states, computational tools are no longer only rhetorical, but they are processes. They simulate and decide. And it is not just CAD anymore. 3D digital modeling, parametric design, generative design, BIM, big data, computer performance simulation, AI, etc. These are all now part of the architect's new drafting board. Through computation, architects are now able to realize the potential that Ivan Sutherland hinted at when he invented the first CAD system, Sketchpad, in 1963. Like the mech suit pictured here, digital design extends our abilities. So, architecture is related to drawing and also very much related to design. Architects design for the future. Necessary optimists, and to borrow from Herbert Simon, architects design to make existing situations into preferred ones. Architects, professionally and ethically, are driven to make a better world, not just for their clients, but for the population at large and for the environment as well. So, given that there is a climate crisis and buildings are part of this problem, they're impacting this crisis, and that design is now done using computation, how can our design technology help us? How can computation impact design to improve environmental performance? This was one of the driving questions for our book, Computing the Environment. The research done for this book comes from both Terry and my firsthand knowledge of architectural design and environmental simulation practices, but also for this book, we carried out interviews with architects and engineers from leading practices worldwide. One of the things that we found was that in every practice we interviewed, architects and engineers were using a whole constellation of different design technologies. Today, building designers must be able to navigate a constantly changing landscape of digital tools. For example, Building Energy Software Tools Index lists 147 software packages just for environmental design. And it's not just using tools, but developing their own tools. The designer has become the tool maker. So, Foster & Partners is one of the world's most well-known architectural practices. Founded in 1967, the practice has made significant impact on both design culture and our built environment. The office maintains a focus on sustainable design, drawing on both vernacular traditions and the latest building technologies. In the late 1990s, the office founded the Specialist Modeling Group, or SMG, to address the growing need for digital design expertise in geometry, building performance, and fabrication integration. I worked at Foster & Partners for many years as an associate partner with the SMG, designing and building projects such as this one here, the Kogard Courtyard at the Smithsonian. However, today I will talk about a Foster & Partners project that I did not work on, the Oceanwide project, a project that was done more recently and contains cutting-edge approaches to design, computation, and environmental simulation. While Foster & Partners uses MicroStation as the primary CAD software, the SMG and design teams use whatever digital design tools are necessary. For this project, a variety of software packages were used. The main structure and geometry were done using CATIA, the interiors used Revit, the facade was done using Dynamo, and Rhino was the go-to 3D CAD sketching environment. The SMG works between architectural geometry and engineering calculations. They develop custom digital tools that integrate engineering calculations within parametric geometry models so that they can more rapidly produce more relevant analysis, going from days or hours to even minutes. Xavier de Castellier, the former head of the SMG, says that the software that they customize sits between hardcore engineering tools and fluffy architect tools. Author Kjell Andersen writes that while design simulation is often seen as a specialist tool for predicting energy performance, the greatest value for architects is the freedom to play with design ideas and receive timely feedback. The SMG has written a custom tool for MicroStation that implements radiance and have created their own wrapper for widely available environmental tools, Ladybug and Honeybee, which they call LadyBee. A key part of the design for this project is at the ground floor where the building has been, quote, lifted up to create a new urban room that is open, accessible, and transparent. The project promotes a sustainable model of high-density mixed-use development. The team used performance simulation to understand the user experience in various ways: light levels, both artificial and natural, glare, the thermal environment, and acoustics. Over the last 10 years, the SMG has developed expertise in computational fluid dynamics, CFD, which is used to predict wind and airflow. A series of CFD simulations were carried out at various places around the tower and studied the influence of various building shapes on wind distribution. Both CFD and wind tunnel testing were done, but CFD offers considerable advantages as it can be completed much faster and in-house. The SMG ran simulations for 16 wind directions, and this data was combined with weather data. They found that the tower was intercepting wind at high level and pushing these winds down to lower levels. In response, the SMG designed a wind canopy so the wind doesn't reach the inhabited level. The SMG also found that the software architects use to compute the radiant environment is generally fairly inaccurate, and so they aim to develop new tools that predict performance with a level of confidence that is reasonable and yet still runs fairly fast. For the urban room, the design aspiration was to make sure the space was comfortable. Using the Universal Thermal Climate Index metric, the team simulated the public space along with similar spaces in the surrounding area for percentages of the year that are comfortable. Xavier de Castellier explains that we find ourselves in a middle ground, creating tools related to design, but that are still really accurate. Acoustic analysis was largely done with a plugin to Rhino called Pachyderm, an open source software that computes performance using ray tracing algorithms. Philip Robinson, the team's former acoustic expert, has found that importing geometry from CAD to commercially available simulation software to be an onerous process. But by using Pachyderm and Rhino, he is able to both design and simulate using the same software, and therefore does not have to bother with translation. As computational tools for environmental design mature, the potentials what teams like the SMG can do with them becomes much greater. SMG partner Irene Gallou speculates that simulation will give young architects a tool to understand the environment and to develop intuitions about the impact of architectural design on environmental performance. Thank you very much. I'm now going to hand it over to Terry Peters.
Thank you, Brady. Thank you, Brady.
Okay, can everyone hear me okay?
Yes.
Yes.
Yes, great. Thank you very much. I am going to continue on and pull out some main points from the Computing the Environment book that Brady and I co-authored. So over the last 10 years, there has been an explosion in digital tools that designers can use. In the book, we examined a history of building performance tools from 1960 to present and created this diagram clearly inspired by Charles Jenks's 1973 graphic of architects and movements. And we looked at the recent history of building performance and simulation tools when they were introduced and really saw this huge explosion in the last 10 years and even increasingly in the last 5 years. So one of the main points that I'm going to draw out of the Computing the Environment book is this idea that of visualizing and visualization leading to understanding. So visualizing data allows us to understand it, to share it. That's how we can communicate and create trust between disciplines. To illustrate that, in the book, we interviewed GXN, which is the innovation group within Danish office 3XN. And talk to them about how they use digital tools, how they use simulation. And this example kind of illustrates that they regularly use environmental simulation on all of their design projects at early stage. And for this example of a new bank headquarters, they worked to take quite an abstract design idea, openness, connecting to the street, connecting to the public. The client's wishes, they wanted to translate this into creating a collaborative, comfortable environment for people working in this building. So how to translate these big ideas into architecture? A key was to use daylight to drive the building's form. In this image here, they used the Velix daylight visualizer tool to calculate the daylight factor for interior spaces, while considering the relationships between building geometry, orientation, views. And you can kind of see in the small photo there, the floor plate shifts in orientation as it moves up. So they used environmental simulation to get them to actually get visual feedback about design decisions. Rather than spreadsheets of data, they had visual graphics that allowed them to better make design decisions to bring them closer to design intent. So in this case, the goal wasn't about minimizing energy use and energy consumption, but actually their goal was for people to use the space, to enjoy the space, to be comfortable. And the client for Swedbank said, some people have been at the company for 25 years and only met each other for the first time the week they moved into the new headquarters. They had never crossed paths before, even though they worked in the same office. So it's this idea that they can use the feedback they get from their simulations to make design decisions to get closer to their design intent, in this case, for collaboration, for openness, for people enjoying the building. The second point I wanted to draw out of the Computing the Environment book is that data can also change behavior. So we can use data to change and understand people's behavior in buildings using real-time feedback. Another project from 3XN is their Green Solution House. It's a hotel and conference center in Denmark. I'm using it to illustrate the idea that some of the new metrics for sustainable buildings and for energy consumption are not easy to visualize. With this kind of data, if you can't communicate the findings, it's sort of limited use. So in this project, inside the hotel rooms, there is actually a dashboard, and it allows you to see in real time how you're using energy, like how you're using electricity, water. What else can you see on this? Sort of energy, light, air, and water use. And it actually allows you to see what proportion of the energy you're using is from renewable sources. And people staying in the hotel room, say they're going out for the day, they can kind of see, oh, I'm still using electricity. That's weird. And they can go back around the room and maybe unplug something or maybe turn the bathroom light off. So it really drives home this idea that people are using the energy in buildings rather than buildings using energy. So this is called the Smart Room Collective Monitoring Project, and it was a collaboration with GXN and Autodesk Research. And it really addressed this idea that visualizing data is a really important part of collecting the data and really putting action to it. So kind of looks at communication of data. And these are the nice rooms at the hotel here. So the third point I'm going to talk about is designing for microclimate. So collecting and using on-site data, microclimate data to inform simulations. Another office that we interviewed is Kieran Timberlake, American office Kieran Timberlake. And they use real-time environmental feedback as a design tool in their projects. We interviewed them about how they use digital design tools, which tools they use, how they use them in projects. And we were kind of surprised to find that in recent projects, they are really interested in collecting microclimate data on their sites. So they're actually installing weather stations on site on different projects. And recently they installed 10 custom weather stations on project sites. So rather than relying on more general climate data, like TMY files for a specific location, they're actually collecting their own data to input into their simulations. They also do some renovations, and they're looking at collecting really accurate on-site, site-specific data about the renovations that they're starting with in order to be able to develop responses that really connect to the existing conditions. And the next point I'll talk about is sharing data. Considering interoperability, workflows with different tools, sharing data. This is obviously a huge issue in practice. In the book, we looked at many digital design tools that practices use in the 12 profiles of offices. We looked at what kinds of sustainable design parameters the different tools account for. And we mapped these into the sort of lead categories and really examined what kind of digital tools people are using. And something we touch on in the book is how we need to use collective intelligence and shared insights to be able to interpret and really use the data that we collect about buildings. Kind of looking at the building performance and the relationship between design intent and buildings in use more carefully so that we can compare them and make better predictions. In the book, we featured Toronto office Diamond Schmidt Architects, and their database for collecting, comparing, and analyzing energy use in buildings that they design. So this is called Ecometrics, and they're able to collect data and compare it across a number of projects that they design in the office. And then they have a really informed starting point for the next project that comes into the office. They already have an idea of what techniques have worked, what are reasonable assumptions to make or aspirations to have about design performance. And this is really rarely done in an office. And if it is done, people weren't sharing it with us. We talked to people about how do you collect and map the building data that you have for all of your projects and compare it to one another. You're collecting all this data. How are you using it? And we think that there are still a lot of barriers about sharing data within offices, even beyond externally. So that I think that's an area that I could see practice sort of developing in the future. The last point I'm going to talk about is, I guess, the idea that it's hard to care about the environment, and it's easier to care about ourselves. So I think reframing sustainable design as design for well-being and design for people is a really important way of getting more buy-in and people making more effort in sustainable design. And I'm thinking, like, what kind of building data would you collect if you were concerned with people's health and well-being, if that was driving the design? And what kind of feedback would you need or want? So many of you are familiar with this idea that in a building, for typical business operating costs, it's not the energy costs, it's not the real estate costs, it's the people that are the valuable asset here. It's training staff, recruiting staff, keeping staff. It's the people, and it's also the people that use the energy in buildings. So really understanding more in detail how people use buildings and the sort of the impact that people have on buildings. So sustainable buildings need sustainable users, yet occupancy and occupant data is really one of the areas of environmental design and environmental simulation that we have the least information for. So many of you might be familiar with the COGA FX studies that in green buildings, people seem to perform better in cognitive tests. So green buildings and enhanced ventilation are really important for sustainable buildings, but also for people's performance in buildings. There's a lot of different aspects that we could explore using simulation relating to what makes spaces both healthier and more environmentally better performing. For example, biophilia, connection to nature, and different ways of looking at lighting. So, for example, in biophilic design, it's becoming more relevant as it becomes a measured aspect of, for example, the WELL building standard and living building challenge. So one of the principles of biophilic design is thermal and airflow variability in spaces. So the subtle changes in air temperature, relative humidity, airflow across the skin. This idea that we can use design tools and that designers should be designing for variability is something that we can do with building simulation tools. And we have new tools like the Alpha tool for circadian lighting, which is a way of measuring and evaluating lighting in buildings that connects to more human-centric approaches. So to sum up, I've talked about some key issues in computing the environment, this idea that visualization equals understanding, data can change behavior, designing for microclimate, sharing data, and we are the environment. Thanks very much.
Thank you so much, Terry. I'd like to invite Tristan now to share his screen and start presenting.
Thanks, Patrick. Just give me 1 second. All right, is that showing up for everybody?
Yes.
Excellent. Okay, so thanks for the introduction, and that was some really great presentations so far. I'm looking to kind of build on that. You'll notice some definite areas of overlap, so I'm looking forward to a really engaged discussion later on. As Patrick mentioned, I work for Intuitive. For those of you not familiar, we're a multidisciplinary firm with primary focuses in structural and building envelope engineering, and operate under a one company philosophy to really allow you to tap into the collective brain trust of our 7 offices spanning 3 countries. That's me. As Patrick mentioned, I lead the building performance analysis team. And so as you can imagine, I'm a pretty big proponent of using simulation to inform the design process. And lately, there's been a lot of discussion around the performance gap and whether or not modeled and actual results should be coming into alignment. And it's really started to bring into question, in some ways, the value of modeling during the design process. So I always like to speak to this by referencing George Box, who was a statistician who was famously quoted as saying that all models are wrong, or actually in some ways famously misquoted as saying that all models are wrong, but some are useful. There's a reason why I riffed on this in the title of the presentation, because it can be the most important thing to remember, and often the thing most forgotten when using simulation to inform a design process. It certainly takes a lot of the hand wringing around the performance gap and makes it somewhat moot, as if you know from the outset that if a model is going to be wrong to some extent, you can stop worrying about it being right and start trying to figure out ways to make it useful. So we all know that as a species, we're collectively facing some pretty serious challenges in the face of climate change. And further, those of us in the AEC industry, as it was established in the first two presentations, our challenge is nothing short of making every building we design net zero in less than a decade. This presents a pretty substantial problem, particularly because architecture, like yoga and the law, is a practice. And it might seem like semantics, but the words really matter here. The design of buildings are frequently based on repeating and modifying past successes. But we don't really have a precedent for a typical, steak and potatoes carbon neutral building that we really need to figure out how to design to address the climate crisis. And so this is where those digital methods that we're all discussing can really come to the rescue by giving us that simulated sandbox to play in, to test our ideas and short circuit history a bit in our development of new net zero precedents. So a few very practical perspectives on how we get there and can achieve our goals. So first off, we need to start asking questions about building performance really early, and literally as early as possible as we can in the design process. For those unfamiliar with the McLeamy curves that are shown here, they're used to illustrate the inverse relationship between the potential impact and potential cost of design interventions as a project progresses. So as you can imagine, on the very left, when things are in concept, you can turn a warehouse into a super tall with a few strokes of a marker on a whiteboard and essentially no cost. Whereas at the other end of the spectrum, once you're post-construction, having a deeply impactful retrofit of a building can be extraordinarily expensive and difficult to execute. Now, traditionally, the analysis of a design's energy consumption was held until towards the end of the design process, when it was felt that there was enough information that an accurate energy model could be prepared. But again, given that we know that those models are necessarily going to be wrong, striving for an accurate prediction of final energy has always been a bit of a fool's errand, and using it as the focus of all sort of modeling work has offered very little value to the design process. So we need to change that. And one of the ways is really going back to basics when we're thinking about how a building interacts with its environment. I'm sure that many of you have seen some versions of this sustainable design pyramid before, but I really like how much it simplifies what we're trying to achieve here. In the earliest days of the green building movement, the pyramid was almost worked in reverse, with solar panels or a power purchase agreement being used to make an otherwise poor design, be green. Much more common have been attempts to engineer our way out of the problem, or engineer our way to high performance by selecting top-end mechanical equipment and complex control systems to compensate for design elements like extensive balconies and floor-to-ceiling glazing. We really need to start thinking passively first. Asking questions from a project's outset about how the envelope, massing, and orientation, opacity, the list goes on, of a building can be used as that first thrust towards low carbon performance. Now, as Terry mentioned, doing so requires taking a look at the climate of where you're designing, microclimate data if you have it available, to evaluate things like total solar resource, how much heat can you get from the sun passively when you want it? And conversely to that, what periods of the year are we really going to be wanting to block unnecessary and harmful solar radiation? How many hours per year can we likely open the windows and allow an ideal internal conditions through natural ventilation? We also need to keep our studies simple. Working Brady pointed out that, rapid and reliable is really where we need to be. And if you're building a fully developed energy model to answer every single question, you're definitely not going to be rapid. So we need to sort of divorce ourselves from the idea that fully developed model is what is needed to answer questions. Setting up simulations to answer a single question allows them to be developed and executed very rapidly, which provides teams with the design feedback that they need in a more timely manner. The images on the slide here are tests that we did, actually tests that Patrick did, of slopes of roof surfaces that were destined to host solar panels to ensure that they were optimized to sort of solar angle, as well as still giving the architectural expression that the client was after. Same story could be said about simulating for depth of overhang and what it can do to the cooling requirements of a space. And similarly, there's a wealth of data that can be extracted from very simple box representations of a single floor or single thermal zone, which again allows for very rapid exploration of high-level design choices. Also, just to make a callback to, I think it was Terry's presentation, that it's really important that we all find creative ways to represent this extraordinary volume of data that is starting to be produced by digital design tools so that it can be communicated effectively with the project team. Parallel coordinate representation has become a bit de rigueur lately, but there's plenty of other methods to make sure that we are parsing these large volumes of data so that project teams can understand them and make their design decisions appropriately. After all, we're not just doing this analysis to show off how smart we all are. Now, so far, all of these sort of simulation techniques and little bits of advice have all been approaches that are about minimizing the operational carbon of our designs, or the amount of GHGs that are going to be emitted through the normal operation of a building over its lifetime, generally indexed to its energy use. This is sort of represented by the yellow wedge that's on this slide. But the red bar at the bottom of the slide represents the embodied carbon or cumulative embodied carbon of a design, which is all, when the building opens, that budget has already been spent. So this is the amount of GHG emissions associated with the extraction, processing, transportation, and installation of materials that are all the component parts of any building. But as we push towards net zero operating carbon, the red block becomes a much more significant portion of the total emissions associated with the project. When we look at our near-term and most aggressive goals in terms of needing to course correct by 2030, it becomes clear that the embodied carbon impacts are crucial to being addressed. This slide just illustrates the concept in a slightly different way. By focusing on energy efficiency, we're shrinking the overall size of the emissions pie, which is good. But if we're not addressing embodied carbon, then we're leaving a bigger and bigger portion of that pie and the potential savings available out of our design decisions. So by addressing embodied carbon requires looking primarily at the building's structural systems, which again kind of complicates matters further, as this is definitely an area of design that is historically adverse to being wrong, no matter how useful. Structural engineers like to know for sure that the building is going to stand up and hold its form and not deflect over time. So there's some good tools that are starting to bubble up to help designers grapple with these problems. One-click LCA, Tally, EC3 have all really started to show some real value and get some real uptake in the marketplace. We've also been working on a simple tool internally here at Intuitive that can help us answer these questions for design teams as early as possible. breaking down a design concept into its simplest forms and applying bulk calculations so that we can get reasonable order of magnitude of the volumes of structural and building envelope materials that will be required for a design. It does so by taking some inputs and answering some conceptual questions about the columns, cores, slabs, and cladding of a building, and then uses those details to compute which subsystems within a building have the highest embodied carbon, which really allows design teams the information they need to take a targeted approach to its reduction. So it's a bit of a whirlwind tour, but I'm really hoping that some of that was informative, and I'm really looking forward to the questions and discussion that's going to come up with the panel. So thank you all for your time and attention, and I'll see you back here in a little bit.
Thank you very much, Tristan. I'd like to invite Shada to start presenting.
Hi, everyone. I hope you can see my screen.
Yes.
Okay. Sorry, just trying to. I don't know why I have the captions on. Okay, there we go. Hi, thanks so much for having me on this panel. It's a pleasure to be among such diverse and talented colleagues, and thanks to Patrick and Claudia for inviting me. I'm a PhD candidate at the University of Waterloo, and I'm going to be presenting one of our research projects that I've been working on over the past year with Intuitive and the past couple of years with the Energy Council of Canada and Diamond Schmidt Architects. I want to give a big shout out to Patrick and the rest of our team, including Tristan, for helping on this research. I'm going to start talking about multifamily housing. That's where we started in our research because of the big problem that we have right now with energy, the energy that they consume, and also they're a big factor in affordable housing. So we have 3,000 towers that were built in a period of time that has now expired in terms of useful lifespans, and we need to address them very quickly. There's a lot of money being invested in these towers in a lot of ways to try to retrofit them. We're seeing a gap in feasibility studies of what to do with these buildings and how efficiently we can address them. Just to give you an idea of the market we're dealing with, so 3.9 million units need to be retrofitted by 2050 in Canada. So that gives us a total market of 1.2 billion just for the feasibility cost, the feasibility analysis cost prior to design. So it's a big problem. Where we come in is we try to create a tool that tries to optimize and inform the client to be able to make better decisions regarding their towers. I'm going to go through one pilot application. The Ken Sobel Tower is currently under construction in Hamilton. It is the first passive house retrofit tower in all of Canada. And in this study, we looked at alternatives of what could have been if we took a more expansive approach. So from all of the identified residential adaptation strategies, we picked out two, so recladding and extending. And we tried to optimize based on energy use, daylighting, life cycle carbon emissions, so global warming potential, and life cycle costs. As a first step, we took the existing building. We defined parameters and grids, and I'm sure we're going to hear more about it with element 5 and how modular construction works. But defining those parameters for modular construction is extremely important, especially when you're dealing with existing buildings. We defined patterns for growth. So where can this building actually grow? How does it make sense with the spatial layouts? And in what direction does it make sense to grow? After we had the modules set, the volumetric modules, then we started looking at panels. So we set out multiple scenarios and picked out what panels need to go where, and we came up with a range of 25 set panels with different widths and lengths. In the next step, we started looking at possibilities of separate unit growth. So with one extension, you're going to have a larger unit, but then when you start to grow large enough, then you could divide up the units and generate extra revenue. I'll get into that later. In the next step, as the algorithm starts to generate design options, then we start parsing through those and eliminate the ones that further not meet our guidelines for design. An example of what that looks like. So with a simple extension, you're increasing the unit, which is great in a lot of cases. The clients that we've talked to, they're examples where a family of 10 is living in a 2-bedroom unit. So from a social sustainability point of view, it's very important to be able to extend some of those units, but it's also important for these buildings to start generating extra revenue so they can have sustainable paybacks. So keeping the same unit but extending to it is the ultimate goal. The next step after generating the design options, we solved for adjacencies, and we're able to assign materials. So floor assemblies, wall assemblies, and roof assemblies, so that we could calculate the energy use and daylighting for each of those permutations. And the life cycle analysis and life cycle costing is also based on those material calculations. We also took into account the structural complexity of these modules. We defined a workflow. A lot of this work was developed by my colleague at Waterloo, Chris Rauch. And so we were able to give a score to each of these modules and then factor that into our life cycle costing and performance. So we ran the model for 2 weeks. We ended up with 600 permutations. Each took about half an hour. And right now here you could see the range of number of module extensions, daylighting, energy use, embodied carbon, and so on. From this interactive tool, we could start to filter out our limitations. For example, 40% and up is the acceptable daylighting range, and so on. From this graph on the right, we're showing life cycle analysis, so global warming potential and life cycle costing. And I'm just showing a chunk of this data to show you that within the same energy use and for the same amount of global warming potential, we could have a range of different design options that vary by cost. So that can start to help a lot of clients gain perspective of what they can do with their money. And then the last step, when we map life cycle costing versus structural complexity score, which is a proxy for the design complexity, we could start to pick out the proto-optimal design solutions that look something like this. So the frontiers are here as an example, and the secondary options are here. This is what our results ended up looking like, 600 of these. So jumping kind of into the future work, we're working towards developing an interface that can streamline the whole process and make this tool easier to use. Right now, it's a whole bunch of different components. And the last thing that needs to be added to all of this is a financial analysis. As an example, what I spoke about earlier, developing new units, extra units, and that revenue can help pay back for this project. So in this example, we were able to generate 45 new units, 2 extra unit types. So right now there's a total of 4 with an 8-year payback, an internal rate of return of 8%, which is pretty good. So in the next 6 months, we're looking for more pilot projects, either new buildings or additions, adaptations like I showed you here. And hopefully in the next 2 years, when we have enough data, we could start to develop predictive models that can even make this process faster. Thank you very much, and I look forward to the discussion. Thank you.
Thank you so much, Ada. Patrick and Nick, could you please start presenting?
Sounds good. All right, can everybody see PowerPoint?
Yes.
All right, thank you for the opportunity to present today. We are Element 5. We are a mass timber manufacturer located in Ontario. Next slide, please, Nick. We're in the midst of a revolution in the construction industry, one which began in Europe 25 or 30 years ago and is now well on the shores of North America. It's made its way all across Canada and is now well into the United States. It's a revolution that's characterized by buildings that are being prefabricated off-site, and rather than being assembled or constructed on site, they are simply assembled on site. This is the Brock Commons building. It's a student residence at the University of British Columbia, and I think this is reflective of the future of construction. It's an 18-story building. It was constructed on a concrete podium, and off to the left-hand side, you'll see glulam columns. So these glulam columns sit on top of the concrete slab, and on top of the glulam columns, you'll see CLT. These are cross-laminated solid wood panels. You'll see one being flown into place there, which sit on top of the columns. More columns, more CLT, up 18 stories. One of the things that's really interesting about this particular building is this is one of the first buildings that had prefabricated envelope panels, which were applied to the outside of it, a mass timber building. I mean, this building was rendered completely weather-tight in 9.5 weeks. And so when the industry saw what was happening with this particular building, it started to take notice. Next slide. The concrete and the steel industries are responsible collectively for about 25% of the world's carbon dioxide emissions. However, when you're building with mass timber, what we're doing is we're leveraging the world's forests to absorb that carbon dioxide and to store the remaining carbon in ever-increasing amounts of wood. And if you manage your forest properly, as we do in Canada, US and elsewhere, and you use wood, therefore, to construct things, and in this case, buildings, you've created a system that's the complete opposite to the concrete and steel industries, which instead spew carbon dioxide into the atmosphere, to one which, in fact, remove carbon dioxide from the atmosphere and store it in the form of these beautiful buildings. Over to you, Nick.
All right, I'll take it over from here. All righty, so, to achieve the benefits of mass timber that, Patrick alluded to in the previous slides, there's a couple different categories of areas that we need to focus on, and element 5 focuses services in all of them. So number one, we want to look at structural design and detailing, and what that means is, either you're bringing on a mass timber engineer, such as element 5, or the mass timber fabricator is offering design assist services to the engineer of record or to the architect to avoid common mass timber design pitfalls. Second category, we have detailed 3D modeling, where to have a successful mass timber project, you need to create a fully developed LOD 400 ready for fabrication model. Which brings us into the third category of production. And by taking that model, the guys at our factory will mad at me for saying this, but you effectively hit print, and then those CLT panels and glulam elements can be built in our state-of-the-art factories in St. Thomas, Ontario, or Ripon, Quebec. And then the last category there is installation, where we focus on creating efficiencies during the construction stage to reduce time on site, which further reduces greenhouse gas emissions. Now, Tristan stole my thunder a little earlier with this McLeany curve, but we're going to use it too. We're going to go through it line by line here. So to understand the mass timber design process, this graph shows time on the x-axis, which is all of the design coordination phases. And on the y-axis is the amount of effort required depending on the curve. So the first line here is the ability to impact cost. There is significant potential to make changes to a design earlier in the design pipeline, but as Tristan mentioned, the further you get to construction or operations, the much harder it is to make that design change. Line 2 refers to cost of design, and it's basically the exact inverse of line 1. As you get closer to construction, if you want to make a major design change, it's going to cost you a lot of money to actually make there and take a lot of effort. Line 3 refers to the typical design process where a lot of the details are worked out in the CD phase. And line 4 is where the mass timber industry wants to sit, where the majority of coordination is done up front. Much like Tristan mentioned, where the focus of a passive design needs to be put up front. If you're looking to move to a mass timber solution, that needs to be something that is decided and coordinated as early on in the project as possible. Common design choices that are chosen for steel and concrete buildings can potentially eliminate the ability to use mass timber as you move throughout the design process. It'll end up costing a lot more for you to revert back. And by getting everybody involved early, you can get all the trades aligned with the design, a detailed design for manufacturing model can be developed, and time on site can be reduced with proper coordination. So now going into the 3D modeling aspect of our workflow, we're going to use an example of our largest project to date, which is the Toronto Regional Conservation Authority headquarters, which of course, given the name of the organization, just had to be built in mass timber. So this is a rendering of our full LOD 400 model ready for manufacturing. We've modeled every individual 500 of the 567 CLT panels, 1,061 glulam elements, and 320 unique connections. Beyond that, every penetration, every screw hole has also been modeled so that all of that work can be done prefabricated in the factory and ultimately reduce time on site. What this requires is intense design coordination with MEP and other trades to ensure every penetration in the structure is accounted for upfront. Where a typical construction would require a lot of these details to be coordinated on site, instead we're coordinating this early on the computer with all the appropriate trades to ensure everything lines up, there's no clashes in the model, and the building can be erected seamlessly. So here is now moving on to the third category, we're going to look at production, and this is a model or rendering of our factory in St. Thomas. And honestly, this doesn't do it justice for just how big this factory actually is. The factory will be fully operational by April 1st of this year. All of the wood that we will be used to produce our CLT panels and glulam elements will be made from Ontario forests, and all the wood will be FSC certified. And when the plant is up and running, it'll be the most automated mass timber manufacturing plant in the world, and we will happily hold that title for about 4 to 6 months until the next one is built. This set of photos might do the factory a little more justice, just to show how big it is. You can now see people next to the massive machines. And what we're showing here is the volume of wood products as well that we can produce. At full capacity, we can produce about 50,000 cubic meters of mass timber in 1 year. And what that means is, we talked about Brock Commons building earlier. When that was built, that was the tallest mass timber building in the world. And our factory has a capacity to produce about 22 Brock Commons in a year, which is incredibly exciting for the amount of mass timber potential. But interestingly enough, in terms of scale, all that wood can actually be regrown in North American forests in about 135 minutes. So we're still well within a sustainable mindset there. And then for all that material, the total potential carbon benefit is about 62,000 metric tons of CO2, which is like taking 13,000 cars off the road in a year. Another image from the factory, just to show the capabilities as well, is on the left there. We have the first item that came off of our state-of-the-art CNC machine, and it's very clear that the CNC work can be very high fidelity. And on the right there, we have our X-Press, which is a monster machine that produces the CLT panels. We can use that to produce some of the largest panels in North America at a total size of 3.5 meters wide by 16 meters long by 315 millimeters deep. Though if you actually need a panel that big, that was because we didn't get involved early enough to coordinate the design. Now, all that being said, one of the problems that we have with the mass timber industry is that we want to avoid being considered a component supplier, because as it was alluded to in the other presentations, every design is different, every project is unique, and so just having a set of components, the way you would have like a set of screws, is not going to be able to use mass timber to its fullest potential to solve the climate crisis. So what we have instead here is images from our innovation center in Ripon, Quebec, which is our other R&D facility, which works with finding unique solutions to a wide array of construction problems to ensure mass timber can be used in a variety of different ways and help use mass timber to help solve the climate crisis. So for example, some of the images here you'll see is our box panel, which is basically like hollow core concrete slabs, except consider it CLT. And the next one I'm going to show is our CLIPS system, which stands for cross-laminated insulated panels. So very similar to the image shown on the second slide of the Brock Commons building. This is our prefabricated envelope system, which is high performance, airtight, and has a CLT layer, the vapor barrier, insulation, and strapping all included. And there is potential for us to also include the cladding and windows and doors, all pre-assembled in the factory so that it arrives on site as one solid element. Originally, this was designed for a mass timber building so that both the structure and the envelope could go up simultaneously, side by side, enclosing the building as quickly as possible. But we've realized and had quite a bit of success with offering clips as a solution to even concrete and steel buildings. Which brings us to our fourth category, which is installation. So if we have done everything right up until this point with all the pre-coordination and planning stages, the mass timber products come to site and can be installed like Lego or K'NEX. As you can see kind of in the top of this image here, all of those glue lamp panels have been pre-CNC'd for all of the connections so that everything slides into place perfectly and there's very little extra work that needs to be done on site. Connections can even be pre-installed in the factory. If everything's done properly, we've seen a mass timber product be able to be erected at a rate of about 8,000 square foot of building area per day with a mass timber solution. So the last image I'm going to show here is another example of how mass timber can be applied quickly to site. This is an image from the Oakville Fire Hall, one of our projects. And you'll notice there we also have our clip system at the top of that wall. But the point I want to drive home here is, all the pre-coordination work for this panel was done, on the computer, off-site, and then prefabricated in the factory. It then arrived on a truck, was lifted into place by a crane, slotted into those connections that were pre-coordinated, temporarily braced, and then the whole wall was installed. So just like that, the entire wall of that building goes up and then becomes airtight really quickly. There's no pesky concrete forming, no building steel stud walls and filling those walls with insulation. All that tricky coordination work that would have added person hours to site is taken from the construction site, put either in the factory or on our computer work. And that is further reducing time on site and reducing greenhouse gas emissions from construction. That's our presentation. Thank you very much for listening. We're very much looking forward to the discussion with the panel. I'm going to throw it back over to Patrick Wadzicka.
Thanks, Nick. Thank you, everyone, for amazing presentations. I really enjoyed watching how that common center of integrated process and information-driven approaches emerged. I will ask you to turn on your videos now for the discussion. But before we start our discussion, I'd like to invite all participants who are participating through YouTube to submit their questions in the YouTube chat, and we will read them to the panelists for you. Don't hesitate to share your comments and remarks in the chat as well. Okay, let's start the questions. So I'd like to, first one I'd like to ask to everyone, starting with Brady and then moving in the order of presenting. If our objective was to build buildings in such a way that it's not only neutral for the environment, but positive for the environment, for the people, and if we assumed that we had unlimited resources, how would we measure success? What would our key results be? Brady?
Okay, great. I just get thrown in first here. What would our key results be? That's a good question, right? So I think, this is like one of these things, where you should ask for, we're like doing these things so incrementally. I think sometimes it's like we can lose the picture of like the big picture. And so I think that having an end goal obviously is like super important to know like where we want to be. And I think that obviously where we want to be is like to have buildings that not only perform well, but that people love, right? And I think that we have to like sort of incorporate both architectural dimensions as well as like engineering and performative dimensions to the work. And so not all of it necessarily is measurable in that way, but buildings that actually stand the test of time. And I think like it's a bit, I think we all want to succeed, right? We all want this to succeed. When I showed that picture of Earthrise, and I think this community, we're a little bit preaching to the converted here. We're all designers of buildings, of the environment, and we obviously all want that very much to succeed. And where am I going with this? And so I think it's in a way, it's like not us that need to be convinced of this, so I don't know what those metrics should be to sort of convince the rest of the world to be able to take on these types of approaches, other than this is like absolutely crucial. That being said, like from where I'm sitting, like in the design technology end, there's still work that needs to be done. If we were to say overnight, okay, yes, go ahead, achieve it, give you all the money and materials in the world, I think we still wouldn't know exactly where to go. So I think that it's going to require studying buildings in use to get that feedback, to make sure that we in fact are doing what we want to do. We talked a lot about simulation today. And simulation is great, that it's a predictor, but it's not the actual thing, right? So that those models that we're using are wrong, as was mentioned. So we need to like look at that with these sort of post-occupancy studies to actually understand what that performance is. Okay, I'll leave it there. Next person.
Yeah, I like it. Terry, would you want to now give it a try?
I think like kind of building on what Brady said, like that we're designing buildings worth renovating. We looked at some of the statistics and the things that we know already, that it's much easier to make these big design decisions for sustainability at the beginning of a process, and super hard to renovate certain things at the end. So if we design things properly at the beginning, that's obviously the way forward. So I think designing buildings worth renovating. And then if we were thinking about, I think like actually asking people, there's a huge lack of that, of actually properly doing pre and post occupancy studies, asking people how their experience of the building is, and building that work into a contract, making that someone's responsibility. Because right now everyone wishes someone would do a post occupancy evaluation, but I mean, who's going to do that and share it and communicate it? So that's what I would say.
Great. Yeah, thank you. Kristen?
Yeah, I mean, so in this hypothetical where with our infinite budget and we've just achieved a net positive building, yeah, I think it really does start to come back to those human aspects, in the sense that that this energy and carbon discussion is very arithmetic in a lot of ways. If you get to the zero-sum game and it's actually been established, then yay for you, gold star for everyone. But then it really starts becoming, to Terry's last point, looking into realized performance. What is actually happening in these buildings? Are we achieving the results that we're looking for? And I think even sort of like looking back at, I think it was the third or fourth point of Terry's presentation, is that all of a sudden the human aspects just become really accelerated to where they should have been all along, as being the most important thing. Is it, and then, for this hypothetical, Patrick, if we're able to do this with no budgetary constraint ever, then aspects of the success are like global human happiness in the workforce and whatnot. Like, has absenteeism just been sort of eliminated as a cost to the white collar business environment? Just things like that. That as you sort of like focusing only on energy is annoying. It's far nicer to focus on so that you don't really feel the EUI of a space when you're in it, but you can definitely feel the space has been really well designed and optimized for human occupancy. So I think it's really that sort of shift that will happen if and when that hypothetical is achieved.
Okay, great. Thank you. Shada?
I'd like to echo Terry's point on designing buildings that can last, they're worthy of being renovated. I think the ultimate goal would be not just reducing carbon, but just reducing waste. Going back to an ecological system where we limit our construction waste. Like it's a huge problem that we're not even talking about as much as we should, because we're so concerned because of energy use and the problem that we're dealing with right now. But 50 years down the road, we're going to be faced with a lot of embodied carbon that we then don't know what to do with. So designing for disassembly, designing for adaptability, designing out waste in construction. Modular construction has a lot of benefits in that way. That can, it kind of fits into that circle. So it's a good thing, but there are a lot of different aspects that can also be considered, like what materials we use, how they're processed and all that. So I think reducing construction waste, keeping buildings in a loop longer are all really helpful.
Patrick and Nick?
I'll start off first. Yeah, can you imagine the creativity in the world if we all believed that things were unlimited creativity? It'd be a pretty amazing world to live in when none of us had self-imposed limitations on our own creativity. But so the reality is that that's not the case, and we are constructing buildings today with limited resources, and primarily the reason why we've chose to build in wood, because it's a renewable resource. And so that's the premise of all of we do. And if we continue to manage our forests properly, and as we do in Canada, the United States, and Europe, and other places, then are we able to build infinitely with wood? Very likely, as long as we manage that correctly. So it's a choice between using resources that are limited and those that are renewable. And that seems to be the smart way forward, I think.
Great, thank you.
Great. Great presentations, thank you. I wanted to talk a little bit about the technology, the tools that we have, and Brady, your comment about the constellation of design tech, and Terry, your illustration of how many tools we have available to us right now, not just for design, but for sustainable analysis. But it seems that over the years, we still see a lot of companies making their own proprietary tools. Do we as an industry really have the technology that we need, the tools that we need, not only in design, but in construction and operations, to significantly improve building performance? And if we don't, what's missing? I think I'm going to start with Tristan, since you showcased your own in-house tools.
Yeah. I think the necessary ingredients are there in terms of, are all the tools necessary out there in the marketplace? In the sense that at my desk, which is becoming a distant memory these days, I've got just a printout that I sort of tacked up, that it was a screen grab from a presentation that somebody made that was just, talking about energy modeling and building simulation. And it's a representation of all the physical processes that are going on in a simulation. And it's like a mimeograph. The physics of what's going on in these spaces is not new. So in a lot of sense, the design engines that are in place are the necessary ingredients. Where the custom tool development, I think, tends to come in is that, it's come up a few times, buildings are annoyingly bespoke a lot of the time. Actually, not necessarily annoyingly, because that's what makes it really interesting too. You know, we're an industry that's almost perpetually making prototypes. So in that sense, the custom tool landscape, I don't think is as much an illustration of, you know, an absence of the right tools being available off the shelf. It's just more that it's kind of like off the shelf is the first 80% of the way there, and then we need to sort of throw in some customization, you know, as it arises in our practice from project to project.
Is that what you found from your research on community the environment?
Hey, Claudia, are you speaking to me?
Yes, or Terry.
Okay.
It came up a lot, you know, the 147 environmental tools, and, you know, the idea that again and again we see companies continuing to make up their own bespoke tools. And so wondering if that's kind of the future, that will always be creating, you know, also making tools, not just creating the architecture or doing the design.
Great question. And I think like if we just sort of look at like a bigger picture, it seems like every generation, like in computation in the building industry, thinks they almost have it cracked, right? But then the next generation comes on and thinks, wow, these guys really didn't have it, and they're developing it more. So I think like I think one of the points is that it's constantly changing, and that sometimes within like this 5-year period that we are sort of looking at, we see some sort of stability. I mean, Tristan is correct to sort of say like that the underlying physics for a lot of these problems remain relatively static, you know, and in my own area of like acoustic performance, like the algorithms are sort of all there, and we can see like all the bits and pieces on the floor. It's just that we're still assembling it in the right way. But I think it would be wrong to sort of say that that all the tools are there. And I think that's one of the reasons why we customize. So, you know, like when I was at the SMG in the early 2000s, there wasn't the tools, but there was the aspirations. So we had to like make the tools to be able to do what we wanted to do. And some of it was off the shelf and a lot of it was customization. And I think that our aspirations are just so much greater than the tools. And I think we're also like in this point of like excitement about using computation, right? So like if we think about like the drafting boards and slide rules and so forth, there's only like so much that we could do with them in sort of tool development. But you know, as Patrick was sort of saying in his intro to this whole discussion, this notion of computation, which is sort of like underlying a lot of what we're talking about today, is really like changed the game. And so we're still realizing the potentials there. And I think we've really only just scratched the surface of what we're going to be able to do with that. I think we're making great progress, and it's so like awesome that we're all doing this and that we're all so excited about it. But I think that we've still got like a long way to go. And it's just going to be an exciting journey.
Yeah, and I think just to quickly interrupt here, and to kind of add to what you said, when we look at Gaudi and his analog parametric computer, how he kind of like connected elements and created relationships. It's not a task for just one tool or one software, right? It's a task for the creator, right? And so in that sense, we have a long way to go, I think, and it's unlimited, even like the potential of the creativity of the human mind, right? I don't want to be too philosophical.
Yeah, and just to sort of like again echo Tristan's point, which about like this bespokeness of all buildings, and that's something like when we're sold like the singular CAD system from the software vendor. I think that's something that up till like now and increasing like that it's frustrating for architects because we want to do something different with every project. You know, we're like sort of combining performant aspects in a different way according to whether it's like impacting, you know, some sort of performance metric or an aesthetic opportunity that exists because of the site, or something that's really important to the client or the culture, you know. And so every building is different, and so we're like bringing together these tools in a different way, and these one package CAD systems up till now, like they're really just not working for architects, which is why we see like, you know, at Foster's they're using 10 or 12 different pieces of software just for one building, just for the design process, let alone all the engineering calculations.
Mhm. Excellent.
Claudia, did you want to add to this, or that we have some questions from the audience actually?
Yeah, we do. Yeah.
There are some really interesting questions. I think maybe the next one could be for Shada. Okay, one is kind of obvious. Has your work been published? So I can share in the chat a link to one of the papers that has already been published, and then the other one is being reviewed, right?
Yeah, so we have a journal article in automation and construction that's been accepted. It'll be coming out soon. And there's a journal at ISARC 2020, conference.
And then there's another question for you. Ms. Shada's work on algorithmic design for dwelling units is great. I'd say it definitely is sustainable, but how well would it fare in terms of architectural value? Do you need clarification for that, or is this question clear?
I'm just going to take a stab at it. Obviously, architectural value could have so many different aspects, right? I'm an architect first, more than anything. So I'm a believer that any of these tools that they're exploratory, they're not restrictive. They're there to tell the architect and guide them and what the implications of their design is. But at the end of the day, people are going to be living in these buildings. So that's the most important thing to keep in mind. There's some quantitative things that we can consider. So for example, daylight. With extensions, the first thing that people ask is what about daylight? Is it going to be affected? So that's a big factor that needs to be analyzed in the process. So that is a problem that needs to be addressed. In terms of natural ventilation and how deep these units can get, something that I just want to mention is that when we're dealing with existing buildings, they're usually not as deep as current standards are set. So for example, the Kinsobel Tower, the entire floor plate is around 480 square meters, if I'm not wrong. And the standard floor plate right now in Ontario is 750 square meters. So so that expansion needs to obviously happen within set zoning laws, but also the depth of these plates, there's a lot we could do with them. I hope that answered the question.
Great, thank you. There's another one for Terry about biophilic design. And the author of the question says, biophilic design would definitely work well, but many other concepts of vertical hospitality have been more about luxury than sustainability. What are your comments on this?
Well, I've recently been doing some research on biophilic design, and I often start with saying it's more than just plants. There are so many aspects to biophilic design: long views, natural materials, spatial variety, proportion of spaces. There are 14 patterns identified by researchers and loads more identified in specific projects. So their biophilic design can be used for good and for not good, I suppose. So it's sort of a set of strategies and ideas. So it can work very well with sustainability, I would say, of course, especially visual and non-visual connection to nature and for example, for stormwater management. But biophilic design is not necessarily a sustainability strategy. So I think there's like more discussion about how it's used and what it's for. But I think that biophilic design, which kind of simply put is people's natural affinity for other forms of life. People like things that grow. We like multi-sensory experiences. This can work very well with sustainability. I've studied it in learning spaces. There's like evidence showing that biophilic spaces that incorporate some of these really create a less stressful and restorative environment where people can learn and remember things better. So I think there's a lot to talk about in terms of biophilic design and sustainability. And I think as it becomes part of the well building standard, as we start to have tools like Alpha to actually, it's the first time we can predict circadian lighting performance in buildings, which is fantastic. Great plugin for Rhino. It's early stage tool I'm using it with my students. So I think we're starting to work towards this. And I think that might be associated with luxury because we tend to implement these in more expensive properties, perhaps, just like sustainability, right? Like, yeah.
It's difficult to find budget for those things and kind of like prove to the client that it's worth investing in it, right? You mentioned, I really liked in your presentation the office that is installing weather stations. And could you expand on? Do you know maybe what's the cost of that, and for what's the time span that they have to do that? And are they implementing, like you said, like a few projects? But is it something that could be scaled, like to that other architectural office could also implement it in their practice, or is it another example of something being very expensive and accessible only to a certain group of clients, right?
I think it depends on what kind of weather station you want. There's probably some of us here who have Googled how much it would cost to put a little weather station on the roof. Anyone willing to admit to that? I've done it. For $500, I could get one that like is good. Like it does what I want. It depends how you want to collect the data. I kind of want it to push to my phone. Like I want to know what's happening when I'm not there. So it depends what you want. It depends how you want to store the data. Time steps is a huge issue. You're collecting loads of different data at different time steps. Are you going to be able to interpret that? But there's good, if you Google how to make a weather station on my roof low cost, you'll find it. But for Kieran Timberlake, it was actually, I was a bit surprised that they said in their 10 most recent projects, they're installing weather stations on site. And this was in 2016, I want to say.
Oh, wow. Okay.
Last time, 17, Brady? I'm not sure when we last interviewed them. So anyway, it's probably increased, right? I mean, but they're really focused on collecting data from the building, not data from the area.
Is that before construction, like before designing? Before,
to inform the early stage design simulations. And I had a student at Ryerson this term that was using, trying to use custom skies in his daylight simulation. So there's an interest. It's sort of part of this quantified self movement of trying to collect really personal, specific microclimate data about your environment or about yourself and your activities. I think it's a direction that a lot of people are very curious about. What's the difference between a customized sky in your daylight simulation and just using a regular preset input in your climate studio or whatever. So.
And for the biophilic design, is it absolutely necessary to, measure that data, continuously? Do you have to, equip your building with a lot of sensor basically, or not necessarily? In order to create that kind of like biophilic environment, right?
It depends what you're trying to create. Like if you're measuring daylight, for example, you could do spot measurements, or you could do, you could collect data over time. It's tricky, but people are doing it. For circadian lighting, there are lots of examples of offices and other places installing a circadian system, like Arup, Toronto has been doing that. So I think there's different ways. Censoring an environment and then collecting data over time is a great way to do it, especially combined with asking occupants and doing spot measurements to make sure you're on track.
I agree. Thank you. I don't want to, and more questions. And there are some interesting ones for timber industry. So I'm going to start with an easy one. There's a shortage of engineered wood these days. Why?
Shortage of engineered wood. Are you referring to the types, certain types of engineered wood, or are you referring to the quantity of engineered wood? I'm assuming the latter.
Let's assume that maybe, because we don't have a way of asking a follow-up question.
Well, there are in some areas, and it, it's as ridiculous as it is to say, with COVID, people are using certain wood products to do things around their home. So that has created an enormous demand on certain products. Like it's, for the longest time, here in Ontario, you couldn't find any pressure treated wood because people were using it to build decks on their home and those sorts of things. But in the industry generally, we're not finding that's the case. There's no limit on the forestry supply. there's, the same sort of manufacturers. There's a limit on, because of COVID, on the number of workers that are working in these factories. So I'm sure that has some impact. But whatever shortage we're experiencing now in the industry is likely very temporary. There's nothing, seriously going on that's going to limit that going forward.
And going back a little bit to digital design tools and data, is your factory going to be equipped with like log computer tomography, or for example, digital wood processing, or using kind of algorithmic processes to scan and determine the most profitable breakup of a log? Are you doing this in your, and how are you managing waste then?
Yeah, absolutely. So, what sort of alluded to that in the presentation a little bit. So, when we're doing our detailed design for manufacturing modeling, right, we're figuring out, like, does it make the most sense to break up, the CLT floor in this panel arrangement? If we do it in a different way, are we able to potentially reduce, the amount of wood, the thickness of the panels? If we change the panelization this way, based on the CNC that we have to cut out for this mechanical opening, are we able to do it in less panels, or do we have to do it in more panels if we do it the other way? So all of that is happening at the design coordination phase. And then we're doing all that sort of modeling in softwares like Rhino, Grasshopper, and then the final model is done in CADWorks. And that is what gets sent to our factory, where it's more or less just hitting print. Sorry, the guy at the factory is going to hate me for saying that, but we take the CADWorks model, we hit print, and then that gets translated into data that goes into our CNC machine, so that all that is cut, as was intended in the model, so that the waste is as reduced as possible, so that it's exactly what we intended it to be.
Excellent.
Hopefully that answered your question.
Curious on the topic of waste. Shada, from your research, were you measuring the amount of waste or in the renovations of these projects? Was that a metric that you were tracking in your design options?
So we did not look at that, but it is definitely doable. There are metrics popping up now. One-click LCA that Tristan mentioned. We have circularity measures they've been around for companies measuring how circular business is. We're now looking at quantifying how circular a design can be. So if you're using wood versus concrete versus what kind of joints you're putting in, putting all that data and quantifying it gives you a circularity score of how much of your building, for example, can be looped back into. So it's definitely something that we would want to look at in the future.
Excellent. Yeah, I'm speaking about coming full circle. Just interested on, Terry, you mentioned in your talk about post-occupancy, and even it's come up a few times about comparing design simulation to what actual operation performance is. And if those studies are occurring and anyone knows, if there are any studies out there that are comparing what has been simulated versus what operational energy usages are and so forth.
I think that data is sometimes collected and less often published. So I don't have a lot of examples of that. And sort of relating to that is sort of obviously thinking about performance gaps and thinking about that gap that we have between how you simulated something would perform, and then you go and you get the energy bills and you're like, what's going on? So I've written about the performance gaps, and they're not always necessarily, for one thing, maybe it's a little bit theoretical, but there are many kinds of gaps, right? It's not just the energy gap, and sometimes it's not always negative. It's just discrepancies in how you imagined, and things change during the process and how something works. But I do think the occupant and the user plays a big role in that, like how we use buildings once we have them. Sometimes at the beginning, it's a renovation for a project, and then actually in the new building, you have double the staff because it took the 2 years, you designed it for a certain number of people, the renovation happens and more people move in than you thought were going to move in. It's like, oh, well, that's one of the reasons for the discrepancy between how you thought and how it works. So I'm working on a pre and post occupancy evaluation of a hospital building in Ontario, looking at the comparison between a little farther back, actually the architect's intentions, what gets designed, the simulations, and then in a year's time, we'll be actually doing some on-site testing and some interviews with people about how the building works. And I think there aren't that many examples of that. You would think that's kind of common, especially for such an expensive health building, where they're already putting so much commitment of time and resources and money. But I think that's a really interesting direction for projects to take, and maybe partnering with academia. Maybe academia can provide some of the time that maybe can't be found in a typical contract, where the architects don't really, or whoever, nobody really has the job of carrying out that comparison between simulation and actual.
Right.
That I'm aware of. Everyone we interviewed said they didn't have a method of carrying out consistent post-occupancy evaluations for every project. Nobody that we saw was doing that consistently. But I'd love to hear from others if they know of projects.
Unfortunately, no. I was going to say, sort of to your point, it's a massive sort of contractual gap that exists, and there's a lot of even some trepidation about doing that retroactive look, because it's like, what if the answer is bad? You know, it'll help you learn a lot.
Probably going to be. It's probably going to be bad, or at least a little. Yeah.
Yeah. No, it's. And I think to your point, you know, the simulation gap sort of looked at, it's like, oh, we had this number and then we got this number and they don't match. And that was sort of the end. It was like, and it happened 150 times. So across lead projects. And that was kind of the end of talking about that one. So I think you're right. Like reconciling what's going on in the real world, and you can simulate the real world. Digital twinning is definitely rise as a method for ongoing operations and maintenance, and keeping that energy bill down, and, you know, model-based commissioning and whatnot. But yeah, in terms of that reconciling between design and operation, it's a big gap, and one that I think, closing is imperative for everyone.
But also touching on that, what you mentioned, Terry, the discrepancy between simulated kind of unexpected, you know, like the behavior and what happens in the future, for example, different occupancies. Is adaptive architecture, like architecture that can change its shape, something that is a direction that is worthwhile exploring? Maybe Brady, you could start or to touch on this.
Hey, Patrick, thanks. Adaptive architecture is certainly an idea that has intrigued architects for forever, and certainly was a topic that we were like actively looking into, you know, at the SMG during the period I was there. For instance, we were looking into multiple collaborations with the artist and engineer Chuck Hoberman. So Chuck Hoberman is famous for designing children's toys that sort of can expand and contract based on a complicated set of linkages. And he was interested in moving this to an architectural scale. And of course, you know, this is an idea that fascinates architects. I mean, this is like very exciting. You know, maybe like, you know, you can see that's like an archigram, the moving cities, and Cedric Price's, you know, ideas about these like changing environments and so forth. And so this is certainly like an idea that's captured architects' imaginations, and we're certainly actively looking into this and designing buildings that can adapt. However, the sort of the operational costs and the fabrication costs of these types of structures are often prohibitive, and also like the environmental conditions in which they have to operate. You know, whether it's like a super hot, dry, dusty climate or a super cold climate, that the maintenance and so forth is very it becomes a huge issue. So there are always parts of buildings that move, right, in some sort of way. There's like doors and panels and these things. And so I think there's like, how do we sort of extend these ideas realistically, you know, to make buildings that adapt? Because there certainly is opportunity there with both adapting to sort of changing environmental considerations. I mean, we live in a climate that has different summer and winter or night and day conditions. And so we're always looking to have buildings that can change for that, but also like programmatically, as buildings change, during the day from one use to another, can we have buildings that adapt? And so I think these are certainly issues that are worth looking into, but that come at a cost, and that we have to be aware of that and not naive in our approaches to designing those.
Awesome, thank you.
Probably have time for one more question.
Yes.
So for Element 5's team, have you guys explored bringing complex geometry designs to mass timber buildings? Is it something that this market demands? What are the main challenges?
I'll leave that one to Nick.
Of course, it's certainly something that we're interested in exploring. I think the challenge really becomes getting a mass timber expert involved early, right? There are some unfortunately, someone once told me that if you can design a concrete panel to transfer load, it's totally possible to do anything in concrete, and it's kind of true. If you can just throw as much rebar and concrete in there, you can get incredibly complicated shapes. But there are limitations to mass timber, and so if we're looking to create intense, complicated geometry, then bringing a mass timber expert on early to understand what those limitations are and then to work within those limitations is absolutely critical. We are exploring at Element 5 the use of parametric modeling and evolutionary algorithms to try and create more complicated structures and more optimized structures. We're looking at figuring out ways that we can help architects start from a very good foundation before moving potentially too far outside of the realm of what mass timber can do. But at the same time, we're also still a startup, and our first factory is coming online this year. So there's only so much that we've been able to get done at this point, but that is something we're looking to explore.
Great answer. Thank you so much. Thanks for the discussion. I would like to wrap it up with one last question for everyone. So if you were to give one practical takeaway to our audience to better design the building, what would it be? Just one. Starting with Brady, and then moving in the order of. Okay, so I'm sorry, Brady. I did
switch it up.
I did it accidentally.
I can start. Well, sure. I think my takeaway would be, or my advice perhaps to do with the design technology is that we don't have to be the victim. We're not at the mercy of design tools. We can in fact become the author and create our own design tools. And I think that's an attitude we should be taking forward. Rather than sort of throwing our hands up in the air, use these sort of questions that we have about our design. This is something that served me well in my career. When I come up against a problem designing a building, man, this takes too long to figure out. There must be a better way. If you get that there must be a better way thing, then it's up to you to innovate that better way.
Great, thank you. Terry?
That's a good question. I would say maybe that there's something in design education called in education in design tools in this area called a credibility gap. And it's the credibility gap is when you do, for example, a daylight simulation and you get an answer and you think, that must be right. I got it from my simulation. And you base your answers on that and you go, I think it would be to try to try to develop an intuition for what kinds of answers you might be creating. So with my students, we do physical measurements and we do simulations. We try to get an intuition for, does anyone here know what a space that's 300 SDA feels like? No, nobody can get an intuition for an annual metric of a daylit space. Not possible. But they might be able to get an intuition of what 300 lux feels like versus 100 lux on a handheld meter. So I would say don't blindly trust the simulation results or the results that your computer is telling you. Try to find a way of connecting it to your own experience, whether it's I mean, I just wrote a paper about how smartphone daylight meters don't work, so maybe don't do that. But try to visit buildings and develop your ideas, connect the digital to the physical, I guess is what I'm trying to say, because we can't always blindly trust the results our computers are giving us. Because interpreting it is the whole battle, right? Is how do you interpret these results? That's my thoughts.
I love it. Thank you.
Yeah,
Tristan?
Yeah, I'd say ask the right questions, or specifically ask very targeted questions of your simulation team. A lot of, the very vague and long-winded answers that have come out of asking energy modelers, what does the model say? Is because that's not really a useful question. What is the impact on overhang depth and the ability to eliminate cooling in the shop? That's a strict question. We can build a rig for it very quickly, simulate and answer. And ultimately, the evolution of a design is just a series of thousands of those questions. So if we can parse them into little things that we can quickly ask and query with a simulation, then it becomes a lot more useful and cooperative design process that can, get us where we need to go.
Awesome. Shada?
I'd just like to add to all the comments and just say that validation is really important, to Terry's point and to Tristan's point specifically. Validating the results that you get within your environment, or using multiple tools to find the variations between the tools, how precise they are. Doing case studies as part of schoolwork or in practice is really important. There are a lot of data for existing buildings, for example, that are public that can be used in modeling to validate what you're looking at. So I think validation is the most important, I would say.
Thank you. Patrick?
Yeah, so, this topic is about design in reference to environmental benefits. So as you can imagine, I'm going to say, think about building with wood rather than concrete or steel, obviously. So, but, one of the challenges we face in our industry is, there's a lot of interest in building in mass timber. And 95% of the projects that we're involved in come to us in not designed in mass timber. They come to us in concrete and steel. And somebody says, here's a design. What's this going to cost me in wood? If you really want to take advantage of wood as a structural element, it's really important to engage your manufacturer as early into the design process as possible. So, every manufacturer can make panels to certain sizes, and every manufacturer is different. So the design really needs, if you choose your supplier early, the design needs to be optimized for what can be produced in the factory. And ideally, what you want to do for environmental benefit is to reduce the amount of waste that you're going to get with those. So you want to utilize as close to 100% of the standard billet sizes that each manufacturer is going to make.
Thank you. Nick?
Yeah, I would say, adding to everybody's point, I think the one thing that it would be good to take away from this is just continual learning, and also strive for continuous improvement. We had the initial question of whether or not we had infinite resources, what would be the target? If the target is still to, achieve net zero, and we, implement everything that we talked about today, design every building and build it in mass timber, we're still not there, right? We still don't achieve net zero yet. We don't, Tristan alluded to this, we don't have a cookie cutter solution yet for net zero. So even if we implement all these things that we've talked about, that are all great ideas, we still have a long ways to go. And so I think just the, implementing of what we know, testing, validating, and making sure that then we learn from that and improve upon it and figure out what the next step is to make sure we hit the goals, I think is incredibly important to not lose sight of. Because once we hit net zero, the United Nations says we have to start looking at, carbon capture. So eventually you got to get to a point where you're not just, building at net zero, but you're also sucking stuff out of the air. So there's a long way to go, and we got to keep learning to get there.
Great. Thank you, everyone.
Really
and I guess we could add to it, or I think Terry alluded in it, like the post-occupancy studies, and that no one wants to share them. I think maybe more of like collaboration and collective effort amongst the designers, architects, engineers, builders, to actually strive for the better. Okay, let's wrap it up. Claudia, on to you now. Let me share my screen.
Okay. All right.
Oh, sorry. I was
Yes.
supposed to do it first. Okay.
Okay.
So just really shortly, we have upcoming events. The next user group, our regular event will be in March. And then we have next similar event to this. It's a PAN event. It's going to be on adaptive data-driven architecture in July and August. Both of them, unfortunately, hosted virtually. So look out for some ads and information.
That's great. Yeah, it should be a good event. The TBMC is going to be spending 2021 with a bunch of working projects. So if you're interested in that or hearing more about that, you can become a member. Just membership's free, and you can hear about upcoming projects. Go to tbmc.ca. And just as we're wrapping up here, the session was brought to you by the Toronto Dynamo user group and the Toronto BIM community. We want to thank our panelists, a great and knowledgeable group of people, great discussions, great presentations. Thank you very much. And thank you all for coming, and we will see you soon.
Thank you, everyone.
Thank you.
Thank you very much.
Thank you.
Thanks, everyone. Bye.
Thanks, everybody.
Thank you.
Bye for now.
Bye, everyone.
Thanks.